Dr. Ellen Williams, who is the director of the Advanced Research Projects Agency for Energy, an exciting new part of the Department of Energy. She reports directly to the Secretary of Energy. What I would like to say about Ellen to begin with is that she and I were ships crossing in the night, as it were, at Caltech. She had just graduated with her PhD in chemical engineering, and I was just arriving a few months later in chemistry, as it were, but the same division. And so we've known about each other's work for a long time and have gotten to know each other more recently in various capacities. So it was really, I'm so grateful to you for taking the time out of your very busy schedule to come here, just as President Cicerone did. And I thought it was a wonderful pairing to hear first about the dire straits that we are in the coming years, but how human ingenuity is going to allow us through the initiatives such as what ARPA-E accelerates to hopefully get us to the point where we stabilize the planet. And hopefully even make it better. She's currently on leave of absence from the University of Maryland, where she's been a distinguished service university professor in the Department of Physics and the Institute for Physical Sciences and Technology since 2000. She has actually been at the University of Maryland in the Department of Physics as a professor since 1991. And she is, after she had a distinguished career at the University of Maryland as a surface scientist, in fact, she moved first out of academia to become the chief scientist for BP. And she was in place for not very long when the horrible oil spill in the Gulf happened, correct? Yes, and so she was, it was a real trial by fire to join BP at that time. And now is, before she joined ARPA-E, she served as a senior advisor to the Secretary of Energy as well. So it is my sincere pleasure and honor to introduce to you Dr. Ellen Williams.
Okay, so thank you for that lovely introduction. It is such a pleasure to be here. Am I audible in the back? Somebody wave? Good, okay. It's such a pleasure to be here. I have a chance to talk about ARPA-E on such an august ceremony and opening of the Andlinger Center, which represents to me so much that's important in what we need to do to address the concerns and the worries that we heard about in the previous talk. So I'm just going to dive right in and tell you about ARPA-E. As Emily told you, it's a very young agency. It was formed actually as a result of a National Academy of Sciences study, the Gathering Storm Report, which among other things recommended the formation of an advanced research project agency in the energy area. So our agency was formed in 2009. Got its first funding, and our mission statement is an unusual one. We're formed on what's called the DARPA model, and we're very much focused on looking for innovation, new ideas, cutting-edge innovations coming out of early-stage science and technology that might be developed to have big impacts in the energy area. And we're supposed to look at energy emissions of all sorts, including greenhouse gases, improving energy across all energy efficiency across all energy sectors, and reducing dependence on energy imports. And to do that in a context of America's economic and energy security and America's strength in technology and technology leadership. So there's 3 points here. One is our 3 areas of focus. One is the point of innovation, and the other is the context of American energy security and economic security. So that structure, what we're authorized to do, sets the stage for how we run our agency. And I'm just going to quickly show you everything that we've worked on over the past 7 years since ARPA-E was funded, and that's shown here. So each of these circles represents one of our R&D programs, and you'll immediately see there's a lot of diversity. Because we're tasked to work on innovation, cutting-edge, new things, exploring and developing, we don't stay focused on any given R&D topic for a long period of time. Each of those circles represents a 3-year R&D program that funded about 10 or 15 projects for a total of about $30 million. And on the vertical axis, you can see how we're spanning the entire energy sector from electricity generation through the electrical grid and stationary storage, through efficiency and emissions, and down through transportation and storage. And each of those circles represents a different program where we saw an opportunity coming out of innovative new ideas in science technology that also met a very strong need in one of our 3 mission areas of reducing emissions, improving efficiency, or reducing dependence on imports. And I'm going to come back to these and talk about them in a great deal more detail. I was disappointed. I wanted 4 or 5 hours, and then I could go over all of them, but I'll try to be concise. So those are 2 points. So we've got the breadth of the program covering all of our mission areas. We've got the diversity and the time dependence of the program addressing our issues of innovation and constantly looking for new things. And then there's a 3rd point, which is our focus on impact. And we always, for all of our programs, ask the question, if it works, will it matter? And you've heard the urgency of the energy situation, that we really need to transform our energy sector. And so if it works means, if it works, if your technology is amazing, if it's outstanding, if it does things no other technology could do before, that's great. But it's not good enough unless it also will matter. And for it to matter, it has to be economically viable. We have to be able to take that technology out and convince people to use it. It has to be at least competitive with the technologies that it's going to displace, and at best, it has to be economically attractive. So that adds a very different wrinkle to how we manage our R&D programs compared to many other funding agencies. And so in fact, all of our projects are managed, that we support, are managed in a very hands-on fashion. Every team is assigned 2 mentors from our agency, a technical mentor, our program director, and a commercialization advisor. And they work hand in hand with the teams from day one to develop their technologies and to refocus and pivot the directions as needed to make sure that A, it's going to work, and B, if it's going to work in a way that has a chance of getting out in the commercial sector. So this is kind of where we position ourselves. Many people have seen pictures like this, which is sort of a little cartoon of what it takes to go from a brilliant idea over on the left-hand side to getting something out into the market and having it have a big commercial impact, which is what we need to do in the energy sector. So ARPA-E's place is we're looking for the brilliant concepts that come out of early stage R&D, and we're going to accelerate them as fast as we can through to the demonstration of a prototype that shows that they really can work and deliver value in the energy sector. So ordinarily we would, let's see if I can make this, is this a pointer also? Okay, so ordinarily we would plan to stop someplace here at the early stage prototype and hope that somebody else would pick up the project and move it forward. We're finding increasingly that we need to really help our teams move a little bit farther on and do some demonstrations that these projects can be scaled up and can meet the durability and the longevity requirements of industry. But I'll show you, in fact, I think it's the next slide, that in fact we're seeing a lot of positive outcomes. And so this little chart, we've been keeping track of what happens to our projects as we fund them and as they come to fruition. So we funded about 475 projects over 7 years. Of those, about 200 have completed their time with us. And we've been watching what happens to them afterwards. Some of our project teams, about 40% of our project teams are led by university PIs. And we've had, to date, 35 new companies formed out of our project teams. A lot of our projects get up to the pilot stage, and it's clear there's going to be a lot more R&D effort needed. And some of our project teams, about 60, have done very well, going to other applied sciences departments within DoD or with the Department of Energy, and getting continuing government funding and also state agencies to further develop their technologies. And then we have 45 teams that actually have gotten their prototype to a stage that's far enough along that they've been able to go out and find private sector investors who are interested enough in their technology to invest in them. And the 45 companies have raised $1.25 billion in private sector follow-on funding. So something's working well. And These are just statistics, they're just numbers, but I've spent the last year and a half diving into what exactly is behind those numbers and what's going on in the technologies. I'd love to spend a lot of time telling you about some of our success stories, but I think instead I'm going to mostly talk about things that are new and coming up. But let me just move on. So moving back here, this is a chart of our project technologies, and I'll just comment that we've had tremendous, wonderful successes, coming out of battery storage all across here, coming out of power electronics, and coming out of understanding the electric power grid. And those are areas where we are seeing big impacts and the potential to have very significant changes in what's going to happen in the future. But rather than talking about what we've done in the past, I'd like to tell you a little bit about what's going on now and what's coming up in the future. First of all, let me just comment so you get a feeling for the diversity of the types of programs that we're supporting. Let's just take a look at 2015. So here's our new projects from last year. So up here under electric power generation, we have ALPHA, a fusion project, looking at ways to accelerate fusion experiments so that we can more quickly test and evaluate new approaches and move them forward. We have Mosaic, a project to incorporate micro lenses into solar panels to more effectively collect solar power. Gensets, which is a project to do combined heat and power in a distributed fashion so that we don't waste the heat that's generated in creating electric power by putting the generation closer to the people who might use the heat. We have Nodes, which is a project to understand how we can better use the electric power grid in a way that basically tailors all of our demand and response activities to need and availability of electricity so that we can use the electricity that we have much more effectively. Charges, a system for testing grid storage batteries and figuring out how companies can make money and therefore be motivated to take them up and use them. ARID, a project to look at the question of what happens to electric power generation under situations of drought when you're limited in how much water you have available to you to cool your power plant. Ordinarily, that causes big problems with power efficiency. We're looking at ways of doing dry cooling without the penalty of efficiency that normally occurs when you go without water cooling and power. Transnet, looking at what can we do in terms of saving energy by drawing on all the information systems that we now have available to us. Google Maps, knowing what's going on with the traffic all the time, knowing where all the different mass transit things are going. Can we give consumers choices that they can make that will help meet their transportation needs, but also minimize their energy use for transportation? And then finally, Cara, which I will talk about in a moment as a new way to look at generation of biofuels. Okay, so what I'm going to do is first I'm going to talk about one of our energy efficiency projects, and it's SHIELD. And today we just announced the award of 14 new projects in this window efficiency program. So I'm going to tell you a little bit about that. And then I will talk about Cara, which is a very interesting program on agriculture and how we can improve the sustainability of biofuels crops. And I'll move from Cara to roots because that's very topical given some of the concerns that we've just been talking about. Okay, I was going to have a circle around Monitor, which is kind of center bottom there. And I probably won't have time to talk about Monitor, but it's a program to look at natural gas leaks and how you can do a much more effective job of finding them so that people can afford to fix them. Okay, so let me jump right into SHIELD. Oops. Oh, there's Monitor. Okay. All right, so SHIELD. So SHIELD is a new program. We're looking at single pane windows. And the little chart on the right there tells you almost all that you need to know. You'd think window efficiency, isn't that an old problem? Haven't we solved that problem because double pane windows are very effective and they reduce a lot of heat loss? But it turns out we lose about 4%, 4 quadrillion British thermal units of primary energy in the United States every year because of inefficiency and heat loss through windows. And half of that is through single pane windows. Just because double pane windows are available, I have a lot of single pane windows in my house. It's very expensive and I actually have a historic house. So I'm not going to go out and replace my old single pane windows with double pane windows. So the question in SHIELD was, what could we do with single pane windows to put in place a way of retrofitting a single pane window that would up its efficiency to the same level as that of double pane windows? And our goal in this project was to basically reduce the losses of single pane windows by at least 50%, which would save 1 quadrillion British thermal units, 1% of US energy use every year. Okay, so let's take a look at what we do here. Now, I said to you that we do these programs with both a technical focus and an economic focus. So I wanted to show you the requirements that we put on when we asked people to propose for these programs. So here's Shields. We had 2 different types of windows types we were considering. One would be a film or a coating that you could paint onto your window, and the other would be a manufactured pane that you could use as a replacement, for instance, when somebody hits a baseball through your window and you have to put a new pane in. And we want both of those. We want the applied coatings to be no more expensive than low emissivity coatings that you can buy now, and we want the manufactured pane to basically not cost much more than it would cost to replace a window with ordinary glass. But look at the types of metrics that we're asking the performers to meet as they address this program. First of all, of course, a technical metric. This is a metric of heat efficiency, how much heat goes out through the window. It's typically, for a single pane window, about 1.1, so we want to cut that in half. We have metrics on condensation, a very important metric on transparency, because people want their windows to be perfect. And so no solution here is going to have commercial uptake if it causes fuzziness or haziness or loss of transmission. And then finally, cost, less than $5 per square foot, and service lifetime, more than 10 years. And so those last 2 things are not the things that one normally would see in a call for proposals from the National Science Foundation, but it's different for us. Okay, so let's take a look then at some of our proposals. And I have to say that for Shields, I think this is a beautiful example of what happens when there's advances in science. Because thinking about what does it take to make a thermally insulating film that's also perfectly transparent, it's a really hard problem. When I heard about this program, I thought, aerogels. An aerogel is a very porous material that's it's basically a solid foam, so it's almost all air, and they're pretty good thermal insulators. But they're hazy because when you make a thermogel, you have a distribution of pore sizes, and some of them are big enough that they scatter visible light. What's different now than 20 years ago in materials science? What's different is huge advances in our ability to control materials at the nanoscale. And so here you're going to see some examples of projects where people are really looking at the ability now to do nanoscale control and keep those pore structures down below the micron scale where they scatter light. So here we're really looking at advances in materials science that are enabling new activities. So we have 14 projects that we selected out of a wonderful set of applications. Several of them involved the use of nanoparticles. So putting ordered nanoparticles or not ordered nanoparticles in a matrix. They're small enough that they don't scatter light, and they are filled with air so that they are very good thermal insulators. So several projects like that, but not all of them, because one of the things that we do when we select our projects is we're always looking for a portfolio approach. We want many different approaches to a problem, because at the beginning we don't know which one is going to succeed. Probably several will, but not all of them will. So we always start with a portfolio. And so I'm going to show you 2 examples that were really unusual, things that we didn't expect that we're very excited about. Okay, so the first one is from University of Colorado, and they're looking at the issue, they're using lessons from nanocellulosic materials, which are very interesting materials, and they can form out of cellulose. You can have these little nanorods that self-assemble into air-filled arrays like the ones shown there. And this team is going to put these nanorod self-assembled arrays into a foam coating and make that into a window. So we will see if they can succeed at this. It looks like a very positive, very low-cost approach. And their first challenge, of course, will be demonstrating that they can meet the transparency requirement. Okay. Second one, very different. This team is going to use 2 layers of material. One is thin layers of a transparent clay-like material suspended in a polymer matrix. And then they're going to top that off with a thermochromic vanadium oxide nanomaterial. And thermochromic means that it changes its reflectivity as a function of temperature. So this coating will be very reflective in the infrared at high temperatures, keeping heat loss from happening, and less so at low temperatures. So again, very high risk, very interesting, creative, new approaches based on our ability to control and understand nanoscale materials in ways that we couldn't even have thought about doing even 20 years ago. So I love this program. Okay, now something completely different. I'm going to tell you about Cara. And so this is a big agricultural program. We've kind of moved all the way from physical chemistry to agriculture. And the issue here is that we continue to believe that biofuels are an important part of the energy future for being able to provide futures in a carbon neutral fashion. But we are also very concerned about the issues of sustainability of biofuels in a world where we also have increasing demands for food production and increasing pressures on food production as we're facing climate change. So Cara is a program to address that, and the point in Cara, again, is to build on really recent advances in our understanding of genetics and genomics and our ability to collect and manage huge amounts of data. So let me just tell you about how this is supposed to work. Okay, the first thing is the sustainability issues. The world is facing increasing needs for food for our growing population and for a population that is going to want better quality of life. People have estimated that we need to continue to have increases in productivity in our food crops above 1%. But we're seeing that the productivity increases that we had been seeing many years ago have been slowing. We're not seeing our crops becoming efficient as much as we would like them to. And at the same time, if we would like to have a significant impact of biofuels on reducing CO2 greenhouse gas emissions, we are looking to have increasing amounts of world agriculture dedicated to creating biomass for the use in biofuels. So these are not very compatible issues. But I'm a technology optimist, and so the answer to these issues is to fix this problem of decreasing improvements in crops at the same time as making the biofuels much more sustainable, increasing their productivity, and making them able to work on lands and areas that are not so competitive with food crops. Okay, so how do we do that? We're going to talk about doing that by plant breeding. Old topic, goes back at least to Mendel. In fact, it goes well back before Mendel, but people just didn't know the rules. But this is basically the idea. You've got a population of plants. They have a distribution of properties. This is their average property. You observe that some plants have a property that you really like. For instance, for our biofuel crop, say sorghum, we'd like it to have a lot more yield, and we'd like it to use a lot less water and a lot less fertilizer. There will be some plants in the population that have that characteristic. How do we find those plants and identify them? It's hard. We have to go out and phenotype them. We have to check their characteristics. It's a very labor-intensive process. And once we understand the distribution here, then we have to understand, in some sense, the link, the heritability between the phenotype that we're interested in and how we do the cross and the breeding to generate the next generation of plants that will carry forward with the properties that we want. So the idea in Cara is that we're going to increase that heritability, our ability to predict which plants have heritable characteristics by doing a tremendously better job of measuring the physical characteristics of the plants. Today, the way that this is primarily done, and it's done mostly by big plant seed companies, and primarily only for a few very large food crops like corn, wheat, and rice, is they plant huge plots of different types of seeds, and then a subject matter expert goes out 4 times a year and samples the crops, and so you get a handful of data points characterizing various characteristics of the plots. You go back, correlate that with the genetic information, make your best selection, run another round the next year, and you keep repeating that cycle over and over again. So the idea with Cara is that we are going to make that first part, the phenotyping, much faster. And we're going to collect not bits of data, but we're going to collect gigabits of data. So what we're going to do is we're going to measure the plants all the time, all sorts of characteristics. We'll measure the same characteristics that plant breeders use now, but dozens and dozens more. So what we're looking at now is a bunch of robots going out in the field, collecting data on the characteristics of the plants all through the growing season, and bringing those back into the lab, correlating them directly with the big genetic databases that we have, and allowing us to make that connection between phenotype and genotype, make the best crosses. We believe we can speed up the process of selecting the crosses for the better plant characteristics by a factor of 2 or 3, and go into breeding cycles and improve our crops dramatically, much less expensively, and much more quickly. So we've put together a program which was just kicked off last summer. We want our phenotyping systems that these teams will develop to be inexpensive enough to really develop crop variations at a level that's available to not just the big seed companies, but to universities, to small companies, so that it can be applied to not just the biggest seed crops. And it has to do high throughput screening. It has to do computational solutions, genetics and genomics. And we also are setting up a program reference data system so people can combine and compare their results. So here's some examples of what we're doing. This is our data reference center at Danforth. They have just set up a huge gantry system carrying a whole bunch of sensors on a moving robotic arm that walks through the field back and forth day after day, sensing all of the plants. And you can see the kind of statistics we're looking at. We're going to go from, I can't read it from the side here, 1,000, tens of phenotypes to thousands of phenotypes in terms of the things that we're measuring. We're going to go down to much smaller resolution in what we can measure on the plants. We're going to do a broader bandwidth of the spectral characterization. Data collection is going to go from bytes to terabytes. I said gigabytes before, it's terabytes. And we're going to do it much, much faster. So that's our central system here. Okay. Here's one of our other teams. This, I think, is Carnegie Mellon. They have 2 different types of robotic systems that are going to run around in the fields, free robots that are going to be doing close-up spectral imaging and visual imaging of the color and the shapes of the plants. Plus, they'll also have a special kind of sensor which is going to do penetrating sensing occasionally on plants to measure their characteristics. Then we have overhead sensors. I actually saw a very funny picture the other day of a hawk that had captured a small drone, and so we'll have to watch out for hawks in this. But they will have overhead sensors that can move back and forth over the fields very quickly and collect color imagery and soil moisture imagery. And then finally, other types of moving gantries, again, that can move back and forth and sample all the plants. So we're very, very excited about this new system and the potential that it has. And we believe that this is going to actually transform what we can do in making biofuels crops more sustainable. And as you can imagine, it also has a great deal of potential and is attracting a lot of interest from the agricultural community as well. Okay, so that's Cara, and now I'm going to go one step farther. This is a program that is just in competition right now. It's called Roots, and it follows directly on from Cara, and I wanted to talk about it today because I think it's very timely. So the idea here is to look at these plants very much the way we were looking at that in Cara, but to go one step farther and think about them specifically in terms of their carbon uptake characteristics. So all plants, of course, take carbon out of the atmosphere, use it to grow their structural elements and their seeds and their fruits, and then most of that CO2 is then released as the plants die or they breed. In this one, we're really looking at the issue of getting more of the plant growth subsurface. We would like to have bigger, deeper root systems to store more carbon in the soil. And I'll show you in a minute a little bit more about what that means. But basically, we want to have the roots grow deeper and store their carbon in the soil. And we've done calculations, and we believe that it is attainable to be able to do this if you had complete uptake, to actually have enough additional carbon storage in the soil to reduce the amount of CO2 equivalent emissions. And this is a different unit than Dr. Cicerone was using. So this is for the US, we release about 6 gigatons of CO2 equivalent per year into the air. This would be an uptake of between 0.5 and 1 gigaton per year. So this would be a huge uptake every year of CO2 out of the atmosphere into the soil in steady state. And this carbon in the soil also has a variety of other amazing properties for farmers in terms of improved productivity of crops. So let's just take a look at what the background for that is. This is a picture that shows for the last part of about 30 years over the last part of the last century of the changes in carbon soil that have been taking place in the United States as a result of agriculture. And in some parts of the U.S., there's been reforestation and there's been more carbon put into the soil as a result of reforestation. But in most heavily agricultural parts of the country, there's been huge decreases in the amount of carbon in the soil. And that is a part of a continuing trend that's been going on for at least 100 years as agriculture has intensified. So worldwide, this 100-year debt of soil carbon is equivalent to 65 ppms of our atmospheric CO2. So that's a huge carbon debt, and what we'd like to do is reverse some of that carbon debt and do it in a way that people are incentivized because it's good for them, it's good for their crops, it's good for their soils. It actually is economically attractive to people to drive this. So the Roots program is set up very much like the Cara program. We need to develop phenotyping sensors. You can imagine that's a very much more difficult issue than it is in the case of phenotyping above the ground because we want to look at the roots below the ground in real time. It turns out that the main route of doing root characterization right now is something called shovelomics. So you dig up your plant and you look at the roots, and that's not exactly something you can do repeatedly with the same plant. So we're looking at development of sensors. We're looking again at the correlation of, at the correlation of the phenotypes and the genetics, and then the plant breeding to develop the better plants. So we're very excited about this. We're just expecting concept papers to come in within the next couple of weeks. I've talked to people as I've walked around the country. There's a lot of excitement about this program, and we're expecting really superlative proposals. So I'll just end then by saying, here's our focus program portfolio. You can see it appears to be all over the place, but there's actually quite a bit of strategy here. And what we do, in fact, in each of these areas is every single one of them, we're looking for at least a quad worth of impact, either in energy efficiency or equivalent reduction in emissions. And each of these over many years is going to show turn on and development of those impacts. And it's very clear that the technical potential is there to drive down the carbon use as we need to make it happen. And then the question then becomes, do we have the technical will and the political will to really draw the fruits out of that? So thank you very much for your attention. You can continue to know about ARPA-E by signing up for our newsletter. You can actually find it if you go to that link, and that will tell you about all of our new programs. And before we release a new program, we always hold a workshop. We ask people from the community to come to our workshops and inform us about their opinions and their knowledge and their subject matter expertise so that we can design the best possible programs. And so I'm hoping I'll see lots of people from Princeton at our workshops and from the Andlinger Center. So thank you again for the opportunity to be here today.
Thank you, Ellen. You know, this exemplifies, you know, what the philosophy that certainly we think about at the Andlinger Center, that you need a portfolio of solutions, and you know, all over the map is absolutely what you need to do, and try many different angles on the same problem, right? That's really great. Questions? Yes, in the back.
I was very interested in the application of robots to improving breeding.
Yes.
A question I have about that is the issue of patenting seeds. Do you have any plans to try and make those new seeds available, or do you see patenting as a way to industrialize it more rapidly?
Yeah. So all of our programs, the performer owns the intellectual property. So in this case, almost all of in the Terra program, almost all of our performers are universities. So they're going to be patenting their robots and so on. And we do, as a government agency, have the responsibility to see that those patents are used. If they're not used by the person who holds them, we are supposed to ask questions to say, why is that patent not being used? So we're looking to get those patents out, and because we're driving down costs and kind of democratizing this process, we're very much hoping to see that the activities spread more widely than the existing small number of players in the seed industry. Yeah.
I'm asking a question from a background of a co-inventor of solar cells about 40 years ago, and they have all commercial solar cells have two characteristics. They were all invented in the huge industrial labs that all have gone, and they took about 30 to 40 years to become commercialized.
Yes.
And I want to your opinion where, for instance, high-temperature superconductivity will be invented and developed so you can transport electricity from day to night, for example. It needs a very broad fundamental research effort in a competitive environment.
Yes.
And then it needs 30 or 50 years to commercialize. You must have thought about it. So
yeah, so we've thought about that. So the broad fundamental work is our infrastructure. So if that infrastructure of fundamental research and development, that investment in basic knowledge, if that wasn't there, ARPA-E wouldn't have anything to work with, because we're drawing on that as the input for what we're trying to advance. We're looking for those investments in exciting topics that are close enough that we can help them move towards commercialization. We do have one project, or maybe two, on superconducting wires to be used in wind power. And we're working with teams that have built on, it's not 30 years, but they've built on 20 years of research and development in high temperature superconductivity, and believe they have a process that they can move forward. And they've done some very nice prototyping, and we're going to see that move out into the commercial sector. To be honest, that first step of moving to the commercial sector tends to be a small step. So our teams will start out with small sales. It's going to take many years, as you point out, for those sales to grow and for the learning curves and the cost to come down. But we can see that with that first step is really feasible in many of these cases.
Actually, if I can follow up on a sort of strategic question about, which I thought about before Sigrid asked the question, but it's really related, which is, how do you decide when you put this portfolio together, what is the metric about time in terms, and what I mean by time is, because you could decide you're going to put money into superconducting cables, but we're not there yet, right?
Yeah.
You could say that you might want to put money into solar fuels, but we're not there yet, right? So, because I noticed on the portfolio, it's a portfolio of mostly to do with electricity rather than fuels, except for biofuels, right?
No, actually. Okay. I'll tell you one, but okay.
But I think that there must be some definite constraint that you have put in terms of your vision as to how far out a technology you can look at and say, oh, that's too far out, so we're not going to have a project in that area.
So, as it turns out, our portfolio actually spans that time frame, has a pretty extensive set of wings, both in terms of short-term and long-term impacts. So we've got a distribution of projects in terms of their timescale. Alpha, of course, is not going to generate a fusion reactor in 3 years, but we feel that we can, in 3 years, do a piece of work that has a significant accelerating effect. And so what we're really looking for is, can we advance this technology in a meaningful way in 3 years? So we have to have a well-defined target and a well-defined opportunity, but we don't necessarily expect that after 3 years it's going to result in a product. Kind of our median is, we'd really love it if it came out with a product in 3 years, but that's probably actually a little bit to the left. Mm-hmm. Yeah.
Ellen, that was a wonderful talk, and ARPA-E is a wonderful institutional innovation for speeding up the rate of commercialization of fundamental concepts coming out of fundamental science. The one thing that the United States has, in fact most countries in the world have not been able to do very well, is to come up with institutions for managing large-scale demonstration projects and early deployment of large-scale projects.
Yeah.
And there have been all kinds of proposals for setting up public agencies, quasi-public institutions for doing that, and we've never gotten anywhere over the last several decades on that. And I wonder if you could give me your impressions as to whether we will ever solve that problem in the United States.
Well, ask me an easy question. It's a really tough question. And we wrestled with this because for $30 million, we're obviously not going to do a very big demonstration process. We talk about how ARPA-E might grow and whether some larger scale projects might be in our future. Some of our projects, and I'll come back to the solar fuels, so refuel right there.
You actually know about that.
Okay, you know about that. Okay, so that's one of that is right now a project where we're going to be looking at ways of taking renewable energy in the form of electricity and trying to really accelerate the development of renewable fuels based on chemicals from air, primarily nitrogen or CO2 and water. We think there's a real potential for making some advances in that area. But obviously, if we do that, there's a whole issue of what then happens with scale-up. In this particular program, we're going to try to ask our teams, we've asked our teams, in fact, to take a look at the issue of, is it possible to come up with technologies that can be more modular, that can break even in cost without going to the billion-dollar scale item. And so that maybe, in fact, is the best answer that I have for you, is that trying to break out of the need to go to such a huge initial investment to get your first technology demonstration going, maybe what has to happen.
Yes.
Question not so much on the science side. You said that all the patents, the IP goes to the inventors and universities.
Yes.
I wonder if NSF and DOE had a stipulation to get 2% or 1% of these proceeds to reinvest in research.
Yeah.
What is the amount of money? Because this is subsidy to
Yeah.
industries that are making a lot of money. So what's your thoughts on that?
Okay. Well, so first of all, I will say that this experiment actually has been tried. It's tried at the the DOE National Laboratories, and the amount that they make back on their licenses is very small. It's a very small amount of money. And it's been tried effectively, and we heard someone saying very, very correctly that most of our large industrial research laboratories are in serious trouble, if not gone. And largely they have come under fire because someone in management made exactly that calculation. Can we break even? Can we actually see a black level coming out of our research and development laboratories? And the basic answer that we see is that there is a long period of R&D funding where you don't make money. It's a complete, it's a sink. And after that sink is done, then things start to pick up and you'll start to make money. But if government's not willing to put in the money in that sink, it's very hard to see, it's very hard for industry to even consider making those early stage investments. And so the turnaround in question then is, if we ask them for an equity, we would get very little, and B, we're asking them to work incredibly hard. About 40% of our awardees are universities, 30% are small companies. These people put their life on the line. They kind of step out of their normal lives and they say, we're going to do this and we're going to try to make a product. And they're working like dogs. And I think that incentive of holding the equity is really important for them.
Thank you, Ellen, for what you're doing. Can you tell us a little bit more about the nuclear fusion project and what you might get out of it in 3 years? What are their concepts? How are they doing?
Yeah, so the nuclear fusion program, Alpha, just kicked off last fall. The concept, there's 2 points to the program. One is that we're looking at an intermediate plasma density regime. So ITER is a very low plasma density regime. NIF is not really fusion, but in some sense it's fusion. It's a very high density plasma regime. There's some thought that there's an intermediate plasma density regime where the path towards a commercial outcome might be easier. So we're focusing, first of all, on that plasma regime and asking people to do experiments to kind of demonstrate yes or no whether this is in fact a better regime for fusion. And we're also asking them to come up with ways to design their experiments, because they have to do a pinch or a squeeze of some point, that are much quicker and much less destructive. So we're looking at ways of developing experiments where the whole thing just doesn't get destroyed every time you do a run. Good ideas have come in. We've funded them. 6 months in, the teams are responding very well. So I talked about this at another talk a few weeks ago, and my answer was, watch the space. In 6 to 18 months, we'll have a lot better feeling about what's coming out of it.
Thank you, Alan, for your talk. Just a follow-on question with respect to Bob and I guess Ellie's question. Have you thought about public-private partnerships and leveraging private monies for long-term projects or large-scale demonstrations?
But to a certain extent, the follow-on funding is in some sense a public-private partnership. Some of our projects that look very good, I mentioned that there were cases where we needed to push them a little bit farther along. Generally, when we go to that stage where we're going to say, okay, we'll help you demonstrate that this can be scaled up or that it's robust enough to survive in industry, we will ask them to have a very serious industrial partner. And so we really work hard on those partnerships. We're very excited and interested in this President's announcement of mission innovation and the potential of more investors who are double bottom line investors who are willing to wait a little longer to see their return on investment. And we have as I said, we have an entire commercialization team whose job it is to try to work this space and figure out ways to move the technologies more quickly into impact.